Dear students, welcome to the first live session of the course Solar Energy Engineering and Technology. In this live session, we'll be discussing the brief content what we have covered so far. So far, we have covered 4 modules. Module 1 is about introduction to solar energy. Module 2 is the solar radiation geometry. Module 3, solar radiation estimation. And module 4, solar photovoltaic systems and its fundamentals. So in lecture 1, under module 1, we have discussed the energy scenarios. Under the energy scenarios, we have defined the different forms of energy and what is the need of energy. Then world's energy scenario is energy mix, from where different energy is contributing. Then in Indian scenario, primarily energy mix. And then what is the share of renewable energy? And then global trend of generation of renewable power, then trends of generation of solar power. In lecture 2 of module 1, overview of solar energy conversion devices and applications were discussed. In this lecture, we have emphasized different routes of exploiting solar energy, methods of energy utilization, and devices for thermal collection and storage, working of PV generator, and concept of solar power plants. That means it's an overview about different available solar technologies for different applications based on the situation. In lecture 3 of module 1, we have discussed physics of propagation of solar radiation from sun to the earth. How solar radiation is propagated from the sun. So when it releases electromagnetic wave, it's a short wave. So when it strikes on the earth surface, then it becomes long wave. It's a heat wave. And also we have specifically discussed what happens in the earth atmosphere. So when solar radiation comes, it strikes on the molecules. And then some are scattered. And then what we'll have something like beam radiation and then diffuse radiation. Okay, so beam radiation is something like, if we consider this is the earth atmosphere and solar radiation is coming from the sun, there's sort of radiation, and here we'll have a lot of gas molecules and then water molecules, right? In some cases, what happens? This radiation strikes on the water molecules and its direction changes. It's like anisotropics. And then when this radiation comes and strikes on the earth surface, its intensity is in reduced form, right? So this kind of intensity is known as diffuse radiation. If the solar radiation comes without disturbances in the earth atmosphere and striking on the earth surface, then what we call it as beam radiation. And if we combine these two, then what we can define is global radiation. That means IB plus IT, right? And also we have discussed the phenomena of absorption and scattering in the earth atmosphere. Also, we have discussed sun-earth relationship, different types of radiation. Also, we have included the concept of air mass. What does it mean when you write AM0? That means there is no atmosphere, right? And this indicates AM0 means this is in extraterrestrial region. So if we say this is Earth atmosphere, then above the Earth atmosphere, what we call is as extraterrestrial region. Terrestrial region, and here what we call it as terrestrial region. Terrestrial region. Okay. So if we have to define air mass, is something like if solar radiation comes and makes an angle with the normal to the horizontal surface. So if it is IBN, and if we write A, B, and C, then what we can write, AB cos of theta is BC, or we can say cos of theta is BC by AB. Okay, so if this angle is 0, that means what happens? This will be 1, right? So it indicates AM1. So AM1 is a situation when sun is at the zenith. Okay, so AM2, that way you can find out what will be AM2. Normally, AM1.5 is very, very important as far as testing of solar collector is concerned. That's a AM spectrum, right? Where theta will be about 48.2 degree. Okay, so at this angle, solar collectors are tested normally. So in lecture 1 of module 2, solar radiation and sunshine measuring instruments were discussed. Like, what are the concerns of solar equipment engineer? It is something like, suppose if someone is asking me for design of a solar power plant for a particular location. So first thing what I should know, like the data of solar radiation. Okay, so once we know the solar radiation data, then we can do the analysis. Like based on the potential only, we can specify what capacity we can install. So if we don't have the data, then what I will do? I will look for similar kind of locations, similar in the sense that climatic conditions. Then I will see if that place is having solar radiation or not. Solar radiation data, I mean to say. If that data is not available, then what I will do? If it is available, it's fine. We can use the data and do the analysis. But if that is also not available, then what I will do? Then I have to rely on correlations, which are developed for estimation of global radiation, diffuse radiation on daily basis or maybe hourly basis. Okay, so that's how these correlations have evolved to estimate the radiation which is falling on a particular location. Also, we must know the instruments to be used for radiation measurement. So, for example, if we are trying to measure this global radiation and maybe diffuse radiation, then we need an instrument called pyranometer. And if we are trying to estimate or measure the direct radiation or normal radiation, then we need an instrument called pyrheliometer. And if we want to know the brightness of the sun, that means sunshine hour, then we need an instrument called solarimeter, or you can say it's a hemispherical bowl. Okay, so we can have these strips here. Okay, So these strips are designed, these strips are something like this. It's called sunshine recorder. Okay. So these strips are designed for a particular month. Maybe no, so January, February, maybe single strips. And these strips are introduced in the groove, and then solar radiation is falling on the spherical glass ball, and then it is focused at a particular point at a particular time. Then it will burn because intensity of the radiation will be very high. That burn trace from say morning to evening, if we know, then from that we can find out what is the sunshine hour. And this instrument is called sunshine recorder. And also we must know the units of radiation, like it's watt per meter square, kilowatt hour per meter square. Okay. And then radiation data, irradiation, irradiance, insolation. So these are the terms we use for specifying the radiation data. In lecture 2 and 3 of module 2, solar radiation geometries were discussed. Under this module, different angles, solar radiation geometry for both horizontal and tilted surfaces, then local apparent time, sun path diagrams were discussed. So it means it's like tilt angle, then we have phi, then we have delta, then we have gamma s, then omega, then theta z. Okay, so theta is the incidence angle, beta is the tilted angle, phi is the latitude, delta is the declination, gamma is the surface azimuth angle, gamma s is the sun solar azimuth angle, gamma is the omega is the hour angle, then theta is the zenith angle. Okay, say for example, if I have to define this together, if I write a horizontal surface here, okay, one more horizontal surface I'll write here, because there are some questions in the discussion forum. So north, south, east, and west. This is north, south, east, and west. So if it is horizontal surface, if solar radiation is falling, and if we know the normal to the horizontal is something like this, this is normal to the horizontal surface, and if it makes an angle, this angle is theta z. Okay, and if we project this on the horizontal surface and it makes an angle, this angle is gamma s, which is nothing but solar azimuth angle, and this angle is altitude angle, altitude. And this is normal to the horizontal. And this is due south. And this is solar azimuth angle. Fine. So this is the case for horizontal surface. If we consider a tilted surface, then what will happen? If we make something like this, this is beta, okay? And if we write, so normal to the horizontal surface is something like this, and normal to the tilted surface is something like this, okay? And sun ray is coming and striking on the inclined surface. Okay. So this should be straight line. So this angle is theta, and if it makes an angle with the normal to the horizontal, then it is becomes theta z, or this is called zenith angle. And theta is the angle of incidence. Okay. And this angle is gamma, which is azimuth angle. Okay. And already you know this angle. So this is 90 here. And this angle, maybe I'll write here, is gamma s. Okay. So that's how all the angles are connected. And if intensity of radiation is IBN, okay, so if it makes an angle with theta, then it will be cos theta, which is the equivalent beam radiation, which is falling on the inclined surface, right? So once we know cos theta, which is functions of all the angles what we have discussed, like beta, then we have phi. So we also have to define what is phi. This is the globe. Okay. So if we would like to know the phi of this location, then what we will do, we'll connect the center of the Earth and project on the equatorial plane, and then that angle what they make is nothing but phi, which is latitude. Okay, so this is phi, and delta is something like if sun is here, if we connect the center of the sun and center of the Earth, and if we project it on the equatorial plane, then that angle what they make is nothing but delta. So this delta actually is 0 in case of equinox, and it is minimum 23.45 on December 21, and it is 23.45 degree on Mars 21. It is June 21. And then equinox day, maybe Mars and September 21, it is 0, right? So we can make a variation of this. So if it is minus 23, it is plus 23, then it is 0. And it goes something like this. It is something like this. So 0 is in Mars, and then September, equinox day, and this is December, and this is in December, and this is June. Okay, so that's how we can find out all the angles, gamma, then omega, and again omega we need to know. So it is something like this. Okay, so this omega is 0 on the solar noon here, and every 15 degree or every hour is 1 hour is 15 degree. Okay, so that means if we travel from 12 to 13, then you have minus 15 degree in the afternoon, and if we are traveling from 12 to 11 o'clock in the morning, it is positive 15 degree, and it is forward. Okay, so that's how we can find out what is omega. So we must know the difference between standard time and what is called solar time. Okay, so which is required for calculation of omega. So once we know this, then we can find out theta. Then we can find out all the parameters which is required for design. And sun path is also very, very important. So in lecture 1 and module 3, correlations and calculation of extraterrestrial radiations were discussed, and what is the need, why the correlations are required, and what are different classifications of weather, calculations of monthly average of daily extraterrestrial radiation, different correlations for estimation of monthly average of daily global radiations, all were discussed in the lecture 1 of module 3. So in lecture 2 of module 3, primarily we have studied the estimation of solar radiation, like correlations for estimation diffuse radiation on horizontal surface and cloudy skies. Because see, sometimes we have radiation data, but these are not in the required form. So we need to convert those data as per our requirement. Okay, so we need to do this kind of analysis. And then estimation of hourly global beam diffuse radiation on horizontal surface on a clear skies were also discussed. And also we have estimated the total radiations, which is something like we have IT. The total radiation means we have included beam radiation, then it is RV, then we have ID, RD, then we have IB plus ID, then we have RR. So these are the tilt coefficient for beam radiation, diffuse radiation, and reflected radiation. Normally, we do not consider this reflected radiation, but when we are doing very precise calculation, then we must include in the total radiation budget, right? So this is something like, no, when radiation is falling on the ground, it will reflect and it will contribute to the heat effect, right? So that's how it is considered. So that's how IT can be considered for calculation of radiation. And then also we have solved sufficient number of numerical problems to get an idea how this can be estimated. In lecture 1 of module 4, solar PV conversion were discussed, like importance of PV conversion and challenges, how PV cells are constructed, how PV modules are, or single cell silicon crystalline silicon cells are manufactured, then working principle of solar cells, then what is band gap energy, what is loss mechanism. These were included in this lecture. So in lecture 2 of module 4, we have discussed semiconductor physics, starting with classification of semiconductors, doping, Fermi energy level, p-n junction, drift current, and diffusion current, then generations of solar cell material. In lecture 3 of module 4, performance characteristics of PV cells were analyzed. Primarily, we have studied the characteristics of PV cells. Also, we have tried to estimate the fill factor, then short circuit current, open circuit voltage, maximum current, maximum voltage, and maximum efficiency. And then also we have derived the estimation of maximum power of a solar cell, equivalent circuit diagram. So how this series resistance and shunt resistance are contributing in the circuit, an effect of variation of solar insolation and temperature on the characteristics of solar cells. And then finally, solar cell efficiency and band gaps were discussed. In solar modules, in lecture 4 and of module 4, solar modules, arrays, and PV systems were discussed, which included discussion on classification of PV modules, effect of shadowing, packing factor, and module efficiency. So earlier, all the cells were something like circular, but nowadays what you see in the modules, the cells were of rectangular shape in order to utilize the space effectively. Also, we have discussed MPPT. It is nothing but maximum power point tracking and possible strategies for operation of MPPTs, PV arrays, and the PV systems. So these were all covered till last week, and 4 modules has been covered so far. And I would like to thank you so much for your attention. And now I'll be happy to answer your queries. Maybe one faculty has asked some assignment 2 and question number 3 about the local apparent time is given and standard time is given, and we need to calculate the standard time is given, local apparent time need to be calculated, right? So as per the calculations, it is comes out to be 10 hours 46 minutes 54 seconds. So maybe if there is a confusion, we can discuss further in the forum. And of course, in coming weeks, all the detailed solutions will be provided for those assignments what already shared. And maybe we have I'm expecting some questions. So these questions, do you have role on fill factor power output of the cell? So if we are having higher fill factor means what? We are getting higher efficiency. That means we are having higher output, right? So that's how it is. We can justify that way. Fill factor, if we write, it is something like we'll have PM, IM, VOC, ISC. Okay, so that means VM, IM, is equal to F VOC ISC, right? And then we have maximum efficiency is something like VMIM is IT into collector efficiency or the cell efficiency, cell area. So this is related to fill factor. That means, of course, this is connected. The assignment to question 3, the answer what is given as per our calculation is correct. Maybe you can check yours. If you have any questions, please ask. Assignment 3, question 12. I'm not sure which question you are talking about. Maybe this can be discussed in the discussion forum. Please, if you have question, otherwise we will stop here. Thank you, Satish. I think there is no questions. We can stop here. So thank you very much for all the students for joining this course. And also I'd like to thank those candidates who have come today in online session. So thank you very much. Take care.